Okay, so let's wait for a couple of more minutes to see if anyone joins, then we can start. Okay, so welcome everyone. This is NOC EE-91 NPTEL tutorial session on semiconductor devices and circuits. The course instructor is Professor Sanjeev Sambandan from IIT Bangalore. I am Debashish Nandi, a PMRF scholar from IIT Kanpur. So today we are at the last session or the 12th week. So far we have covered almost the entire course. Today it will be like a kind of pre-summary session. So let's begin. So the prerequisites and the decorums are as always. So this is 12th week. Okay. So let's begin. Okay. So the question, this question is about the non-crystalline semiconductors. So far we have discussed about crystalline semiconductors, right? The periodicity of the semiconductor, the atoms in the crystalline semiconductors give rise to the concept of your energy band gap, and those band gaps are ultimately linking to your conductivity modulation by doping, and that is the major desired property out of semiconductor which you want to achieve. But what about these non-crystalline semiconductors? You see, there are certain semiconductors uh, like your IWO, IGZO. These are kind of some semiconductors which are non-crystalline but shows semiconductive kind of properties. Okay, non-crystalline, and also you see there are certain kind of organic semiconductors also present. For example, we can have pentacene. These are the organic semiconductors which are also by default these are non-crystalline, or the better word to be amorphous organic semiconductors. So you see in a crystalline semiconductors, what are the difference between let's say this is a crystalline structure. So what you will have? You will have a periodic arrangement of atoms throughout the structure, right? And what about your polycrystalline silicons? Polycrystalline silicons will have, this kind of grain boundaries where in one grain, the this atomic arrangements will be periodic. So we can say that these are periodic structures of some certain portions which are connected or joined through some virtual boundary called grain boundary, where the periodicity breaks. Okay, so this kind of structures are generally known as polycrystalline. What happens when you have a semiconductor which is doped, right? Suppose if you are going above your your NC and NV, effective density of states kind of doping, or you are for some silicon, let's say you are going beyond 10 raised to 19, and those higher doping, your device starts to become polycrystalline. And what happens when you are crossing the atomic density of the silicon, which is 10 raised to 22 per centimeter cube, 5 into 10 raised to 22, then you will have the issue that your solubility limit is then it will solubility limit means you have what is the purpose of your doping, right? A purpose of your doping that you have a silicon crystal, and then you will have certain kind of doping atom sitting far from each other randomly. Okay, so your 10 raised to 17 per centimeter cube per cc doping means 1 in 10 raised to 5 or 1 in 1 lakh of silicon atoms, one dopant atom in 1 lakh silicon atoms. Now what happens when silicon atomic density is your around 5 times 10 raised to 22 per centimeter cube. So if you have your Na or ND greater than or equal to your 10 raised to 22 kind of limit, then you will have a, you have a solvent and a solute, right? So your then your silicon atoms and doping atoms will be almost similar. So it will start to create alloy. It will not remain a semiconductor, it not remain a crystal or nor remain a polycrystalline silicon. Okay. So this an amorphous kind of semiconductor means there is no particular arrangement of atoms. Okay, it is just random. So these are called amorphous or non-crystalline, non-crystalline semi non-crystalline structures for the time being, let's say. So can you tell me why do we require polycrystal non-amorphous silicon amorphous semiconductors in the first place? Any idea from the discussion professor had in the lecture session? Yeah, any idea? Parth Sarthi?
No, sir.
So you know what happens in your you have these LED panels, right? These LED panels, these are large area semiconductors or large area devices. Large area devices. You must have seen that there are now television screens which are almost 120 inches, right? From LG, Samsung, Panasonic kind of stuff. So majorly LG creates these glass panels. So what they do, they take a what is a substrate for our conventional semiconductors or crystalline semiconductors?
Silicon.
Silicon, right? But you know about the cost. Do you have any idea about the cost of that silicon substrate wafer? That silicon costs very high, right? The process of lithography and fabrication is, or the clean room fabrication is very, very high. So you cannot afford to have, you see, what is the purpose of that providing so much integration into a chip? The purpose is that one thing is that you want to get higher functionalities or complex functionalities, and the other thing is that you want your the cost to your these silicon wafers are very costly and the process is very costly. So for this LED kind of stuffs where you need to deploy some kind of circuitry through some kind of transistor action, you cannot afford to have the silicons. Okay. So what they do, they take actually your glass substrates. Okay. And on top of that, they do processing, which I will not go into detail. Let call it, they will do some spin coating or some inkjet printing, okay, of this kind of organic semiconductors or your non-crystalline semiconductors, and they will create layers and patterns which will act as transistors. Fine. So what happens is that, so this LED panels, what you see, you know that this OLED, O stands for organic. So depending upon multiple types of your organic substrate, it's just a liquid organic semiconductors. So you can coat it and you can create LEDs. What are the LEDs? LEDs are nothing but these are diodes, right? If you have a certain voltage, so electron jumps from a conduction band to valence band and it will emit the energy in terms of light. Okay. So these large area devices is generally made with this amorphous semiconductors. Okay, so there is a very different course for this kind of structures or semiconductors, and the main transistors are called generally thin film transistors. Okay, thin film transistors, which are the building blocks. In case of our conventional silicon or CMOS process, we have MOSFETs, right? So in this case, these are TFTs. So there is a whole different branch of courses dedicated to this. So the point I was trying to make is that suppose okay, so for example, the courses in IIT Kanpur, in IIT Kanpur, if you are enrolling for microelectronics and VLSI, a master's course, so you will be given option to choose from this kind of organic or flexible electronics. Okay, so in this kind of courses, they teach this all the physics and all the applications and fabrication processes of this kind of stuffs. So this may not be glass. Okay, so this may not be glass. It may be your, the bottles are made of these PET elements, PETs, plastic, and all. Okay, so you might have been seeing the foldable displays nowadays, right? Because from that point of view, the term flexible has been introduced. Okay, so the device physics is quite different from what you have studied in the crystalline case. So, what is the advantage of the crystalline semiconductors? How did we model the transport? We model that in a crystalline semiconductor, the electron travels just like a free electron. Remember, but what was the catch? Can anyone tell me? Transport of a transport of an electron in a crystal periodic potential can be modeled by, or we did model it by free electron transport, right? But what was the catch? What did we
Use
change?
M star.
Right, exactly. We used M star instead of the rest mass of the electron, right? So this M star, how did we find out this M star? This come down from the your band structure, right? How did your bands are there along the various symmetry points in the crystal? From that, you remember that your M star is h bar square over d square e by dk square at certain points, or the minimum energy points to be precise. Okay, let me get it. Minimum energy points. Okay. So, but in case of organic this amorphous semiconductors, you cannot use the same kind of transport model. Okay. So what happens in organic semiconductors or these amorphous semiconductors is that you have your individual atoms sitting. Okay, you will not be forming any such kind of bands or continuous space. Remember that we model the chronic during modeling the chronic penny model, we had something like that. So there is one well. These are the wells, and let me just highlight. So these are the wells ones, and then there is a larger well. So what did we model that in this place electrons can move freely, roam around, right? So in case of these amorphous semiconductors, this kind of analogy or derivations are not possible. So what we generally do is that we discrete molecular or individual molecules will have your individual these bands. So these are generally called, these are called HOMO and these are called LUMO. So what does HOMO stand for? Highest occupied molecular orbital. Okay, and this stands for lowest unoccupied molecular orbital. Fine. So what happens is that suppose you have a electron, some electron has jumped from this place to this. So you treat it as a model of conduction band, but which is not continuous. Remember that, and you can think it of as a. It is just for thinking. Okay, you can think it of as a this EC and EV. So how will, suppose now if you apply certain electric field, let's say you have applied electric field across the material. So how will the electrons transport? The electrons will transport, and there are also presence of this kind of defect states, random defect states. Okay, these are, let's say, your defects or traps. Okay, so and by the way, why do we have this? Can you guess why do we have higher amount of defects, more defects in this kind of amorphous semiconductors than your crystalline silicon? Any guess? Random guess would be fine.
Grain boundaries due to.
No, no, grain boundary will be there in the polycrystalline thing, right? In the amorphous thing, there are, see, first thing, understand that if you take a silicon, raw silicon, right? It will be, it will have defects. Do you agree with that? How do you remove those defects? You heard about this kind of fabrication process like Szoralski and all, epoxy, this how you draw the silicon wafer and then melt it and then draw the silicon wafer. So there are some purification steps or more costlier steps to get the silicon, the wafer, the silicon which is used in the silicon wafer for fabrication. Okay, that is almost very pure silicon. Okay, that fabrication steps requires first of all time, second of all money, and third of all multiple expertise. Okay, but in this kind of organic semiconductors or your amorphous semiconductors, you can make in your if you have proper arrangement, you can set up a lab yourself. Okay, it will, the cost difference will be like 1 in 10 raised to 4. That level of cost difference is there for per unit of chip. Okay, so due to the non-stringentness of the fabrication process, you have the defects, more defects in case of these organic semiconductors or amorphous semiconductors. Okay, so what happens is that, now tell me, how will this electron travel? It needs to, suppose this is your one plate, plate 1, and this is your plate 2. So plate 2 is kept as higher potential than plate 1. So now your electrons need to transport from this place to plate 2 to plate 1 to plate 2. Fine, because electric field is in the opposite direction. So how will those electrons travel? So generally what happens is that these electrons hops, okay, from one place to another place, and this hopping depends on many things. This is called hopping of electrons. This hopping depends on many things, but say first of all, it is a kind of thermoionic process. Tunneling may be involved. Also, your trap states or defect states, traps may assist in transport. Okay. So what do I mean by traps may assist in transport? That suppose you have a trap state at this location. So what will happen that this may drop here, and then upon excitation or getting some non-zero temperature, it may get excited and reach to the right hand side your LUMO level. Okay, so this way electrons will travel. So what is the first thing coming in your mind? That the mobility of this kind of devices or this kind of semiconductors will be much lower. Okay, so mobility in amorphous semiconductors will be lower, even much multiple orders lower. Okay, so by the way, what is the mobility of electrons in silicon? The number, the value, anyone? Yeah, you have a, you can guess it, right? You may be wrong. What is the value of electron mobility in a bulk silicon? Yeah, Parth, can you answer?
No, sir. Didn't remember.
These figures you should try to remember, right? It is around 1350 centimeter square per volt second. And what about the holes? Holes will be around your 450, right? So you remember that why this kind of difference is there?
Due to mass,
No,
effective mass.
effective mass, right? Due to the difference of effective mass. And also, can you tell me what is the mobility of electron in MOSFET channel? This is in bulk silicon, right? So, by the way, what does affect mobility? What do you think?
Scattering.
Scattering, right? Exactly. So, do you think that in a bulk silicon or in a MOSFET channel, in which case the scattering will be more?
When impurities are there.
Uh, okay. My
A
question was
surface
that
is rough.
exactly. So, there is a rough surface sitting, right?
Yes, sir.
In case of MOSFET, so there is a silicon dioxide and silicon surface, and the electrons are near that surface only. So what happens that due to surface scattering, the mobility of the channel electrons in a MOSFET is maybe you can get maximum up to 300 centimeters square per volt second. So you see the difference in bulk silicon and this MOSFET channel. So if somebody asks you that what is the mobility of electron in a silicon, so what will be your answer? You should ask that tell me which case you are talking about. Is this you are talking about bulk silicon or some kind of electrons in sitting in nearby some channel, right? Nearby some interface. So depending upon that your answer will change. Remember that. So mobility in this kind of amorphous semiconductors are very less. So what happens actually that suppose you have a trap here, okay, let's say this is a trap. So once a electron is trapped inside a trap state, it is a very statistical phenomena that after what time they will be released. Okay, so it is not that simple that if an electron is trapped, it will be released immediately. It is not like that. The electron may get trapped for eternity. Okay, So these kind of traps are called slow traps or fast trap states. Okay, so the purpose is that the purpose of this discussion is that the mobility will depend on how much time the electron spends in conduction band, okay, or your this LUMO level. So suppose if your all the electrons are to be there in the conduction band all the time, then your mobility will be higher, right? Because these electrons does not take part into drift transport. For that you need your electrons in the conduction band, right? So your mu drift or the total mu will be percentage of time spent in conduction band multiplied by your conduction band mobility. So by default you understand that conduction band mobility mu conduction is much higher than your mu drift. Okay, this is the effective mobility. Okay, so in our question it is given that 10% time the electron spends 10% time in the conduction band and the drift mobility is this. So they want us to find out the conduction band mobility or the free carrier mobility, right? So we can easily do that. Mu drift is given as 2 centimeter square per volt second. This is given as 10% times mu conduction. So what will be mu conduction? It will be nothing but 20 because 2 over 0.1 centimeter square per volt second. Fine. So this will be your right answer. Okay. So I know that in this course the TFT part did not was not covered very depth, but that is how it is. This course just to give you the flavor or the knowledge that there is an existence of the other kind of transistors or the TFTs, thin film transistors. Okay, so these kind of transistors are important in your mobile displays, in your these displays, whatever you say, in your computer displays, in your TVs, all large area devices. There, this kind of TFTs are used. Okay, the pixels you know about pixels, right? What is a pixel? A pixel is a cell made of certain TFTs, capacitors, and all. And accumulation of the all the pixels will give you the entire RGB of your entire screen. Okay, so there is a whole lot of story and a whole lot of depth in that domain, but please keep that in if you are interested in for higher studies in this flexible electronics domain. So there obviously will get in-depth analysis of that. Okay, so that is all about problem 1. So let us move to problem 2.
Sir,
Yeah,
and sir, what is hopping?
hopping means hopping means you have heard about the long jump, right?
Yes, sir.
You, so suppose a person is not walking, but a person is jumping and then moving, right? Should I put it? Hopping means uh, in communication also you must not have heard it because they do not cover it in the undergrad. So hopping means you put a step and then you jump, put another step, then you jump, put another step. Okay, in that way you are moving. That is called hopping. Okay, so hopping means that moving in our case, hopping means moving of electrons from this place to this place, this one LUMO to the nearby LUMO. But in case of crystalline semiconductor, what was happening? This was a continuous band. The EC was continuous, right? So you can basically, the electrons can basically have a random thermal walk in this. They do not hop, but they walk. It is the terminology, how we express the movement of the electrons. Okay. But in actual hopping means like that you are jumping and walking, jumping and moving forward. Okay.
Yes, sir. In MOSFET, professor had said we didn't consider hopping.
Yeah, we didn't consider hopping because we didn't have this discrete LUMO levels, right?
Yes, sir.
We had a continuous EC. How did I draw the EC for this was my semiconductor, crystalline semiconductor notions, right? These are the crystalline notion. Okay. But in case of this, what I am drawing? I am drawing EC as a this kind of discrete states, right?
Yes, sir.
Okay. So, okay. So let's move on to the next problem. So it is asked that assume an n-type thin film transistor. There you have the term thin film transistor n-type, which is in which the trapped electron concentration is much higher than the free electron concentration in the above threshold operation regime. The electrostatics is dominated by dash and the drift transport under the drain bias dictated by dash. Okay. So now tell me for this question, for you to answer this question, you do not need any knowledge of the amorphous semiconductors. Now tell me what do you understand by electrostatics? What is electrostatics? Electrostatics means your charge is stationary, right? It is not moving. So if you have a positive charge, let's say, you will have a field around it, right? What electrostatics tells us that how any other kind of charged particles, this is I am using for holes or positive charges, let's say, and this is for negative charges. So how another this will get repelled, this will get attracted, right? How another charged particle moves about about any electric field, that is called electrostatics. So what are the laws governing electrostatics? Laws governing electrostatics, any idea?
Gauss law.
First one is absolutely right, Gauss's law, right? And what is that? That is del dot D is equal to rho. You are comfortable with this notation?
Yes, sir.
In one dimension, it is nothing but rho, or del dot E is rho over epsilon. So, okay, if a good thing to tell you at this stage, what are the differences between these two laws? Are these two laws always equivalent? That means D equals to epsilon E. Is this always equivalent? you will get some more depth of this in this discussion. Okay, so I will suggest you to interact for this part.
I don't know.
No, just try. Let me try to develop some analytical skills for you. Okay. So, how do you know that uh, even if you do not know anything about the physics, if some blunt questions like this come in your way, how will you tackle that? So, first thing that uh, make it comfortable for you. So, what is more convenient? You know about this thing, right? This D is equal to rho. Fine,
Yes, sir.
one dimension. Now, tell me, this is epsilon E times rho. Now tell me whether I am right or wrong. Is this okay?
Yes, sir.
So,
If mate,
yeah.
yes, sir.
Go on.
Yes, sir.
No,
If
no, go on. We were telling
epsilon
something.
material epsilon changes or not change.
Yeah, exactly, right? So, there are materials where this epsilon is not constant. It is a function of the your dimension or x. Then this is not equivalent, right?
Yes, sir.
So, in case of isotropic or homogeneous materials only, this E is your constant, right?
Yes, sir.
In case of homogeneous materials only, this is constant. So this term becomes 0 and you can write this equals to rho over epsilon. So remember that always, that if such kind of questions come into your way, you can answer that. Okay. So this
Yes,
has
sir.
nothing to do with whatever you do not know. You knew everything, but this is to develop how to think and how to answer the questions. Okay. So this is very important, and this assumption we always make, but we do not spell it out. So it is difficult for you to catch always. But keep that all the assumptions. A good engineer always keeps all the assumptions back of his mind. Okay.
Yes, sir.
So remember that. So now tell me, uh, this row, does it need to be free, or it can be anything? Free means, does it need to move or roam around or hop around, or it
No,
can be anything?
anything.
It can be anything, right? This
Yes,
row
sir.
is due to, may say, moving plus your stationary charges, right? So you see your electrostatics, and okay, let me just draw the diagrams also. So for you to be, let's say these are the trap states, and let's say certain amount of electrons are present here and very small amount of electrons are present here. Okay, so your electrostatics will be governed by the entire thing. Your electrostatics will be governed by both trap plus free charges. Do you agree on that?
Yes, sir.
So, and it is mentioned that your trapped electron concentration is much higher than your free electron concentration. That means what? trapped plus free is almost equal to trapped. That means the electrostatics is governed by what? Trapped electrons. And what about the drift transport? What do you think? What about the drift
Uh,
transport?
Free electron only.
It will be due to free electron. And why?
Drift needed mobile charge carrier.
Exactly. Drift needs mobile charge carriers, or the carriers should move along this conduction band, right? From this place to this place. Drift is what? This is a higher potential. This is a lower potential. So there will be electric field. So electron will move in this direction, right? And this movement of electron will only be happening through the or on the conduction band itself. So drift transport will be dictated by the free electrons. So this will be your answer. Okay. So the main point of this is that for you to understand that electrostatics is governed by this rho, and they have written here that Poisson's equation, right? And what about this Poisson's equation? This is nothing but Gauss law only. D square phi by dx square is equal to minus rho over epsilon. Just if you put E is equal to minus d phi over dx and substitute to this equation, you will get this. This is your Poisson equation. Okay. So this is how it is. So I think it is clear. So let's move on to the next one. Yeah, continuity equation. So what is continuity equation? You can directly tell me. What is continuity, by the way? Means how did that name came from?
Flow should be constant.
Flow should
In
be constant.
input is equal to output.
Input is equal to output. Okay, very close. Let me just try to explain. This is a semiconductor block. Okay, so let me take a very thin strip. So this is a very thin strip, okay, of the semiconductor. So for our convenience, let's take that this area, the cross sectional area, is unity or 1. So you have certain amount of potential applied. So in this is, let's say, bulk semiconductor. Okay, so you have transports of the form drift and diffusion. Okay, so let's say some potential difference exists at this place. So some current will be entering this location and some current will be exiting this thin strip. Okay, so let's say this is your delta x and this point is x. So this point will be x plus delta x. So current coming in, or the current density coming in the this point will be your Jp. Let's say we are discussing about holes only. Electron continuity will be the similar thing. it will be JPX, and the current coming out at this point will be, let's say, JPX plus delta X, because this point is delta X, this point is X plus delta X, this point is X. Okay. So now what is the law of conservation? Law of conservation will tell you that net rate of increase of carriers in the delta X times 1 is your area, so it will be a volume. This volume will be equal to what? One thing is that the amount of current entering may not be equal to the amount of current which is output or exiting. So that means if the exiting current is smaller, then that means there is some carriers are accumulating. Okay. So your carriers due to current flow, per by change in time plus in this region there may be generation of carriers. So generation of carriers, let me just bring it down, it will be easier. Generation of carriers in the volume minus recombination. With generation you get electron hole pairs, that means your carrier number of holes will increase. With recombination your electron hole pairs annihilates, that means your holes, number of holes will decrease. Okay. Recombination in the volume. So how do we quantify it? Rate of change, we quantify it as this times delta X times 1. This is the rate of change. dP is the excess carriers over and above equilibrium. We have discussed this, right? dP is excess holes and carriers due to current flow. Carriers due to current flow per charge per change in time. How will you accommodate that? Change. Okay, just let me write it here. Change in uh, change in carriers equal to change in charge over Q. Do you agree? Because your Q times carrier is your charge, right? And your, then what will be your rate of change? Rate of change will be what? Rate of change of charge by Q. Rate of change of charge is what? Current by Q. If you have unit area, then current is becoming current density over Q. Fine. So carrier due to current flow and that rate of change of that we can write as 1 over Q times net change in current density. and that is your J of, what is the input? Input is your Jp of x. What is output? Jp of x plus delta x. Okay. And if generation rate is G, then delta x times 1 is the volume. And if recombination rate is R, so this is your generation rate. This is your recombination rate. Remember that the equivalence of right hand side and left hand side is of carriers, not of charge. So this is taken care in by 1 over Q for the case of current turn. So now you can write del P over dt, and if you take delta x in the right hand side denominator, you will have 1 over Q Jp of x minus Jp of x plus delta x over delta x plus G minus R. So you have dp of dt equal to 1 over q, and this term you know that if delta x tends to 0, in limiting sense, it becomes minus djp of x over dx. Because limit delta x tends to 0, jpx plus delta x minus jp of x over delta x is nothing but dj over dx, djp over dx. Okay, so this is the basic definition of differentiation. So you have your equals to minus 1 over q djpx over dx plus generation minus recombination. This is called your continuity equation. What is the significance of continuity equation? The significance of continuity equation is that it tells you a situation where your device is not in equilibrium and all kind of current transports are there, and you are taking into consideration generation, recombination and steady state. Okay, that is very important. So you have your this. So what will be the answer for continuity equation? We have rate of increase should be inflow minus outflow. Okay, let me just write it down. This is rate of increase. This is inflow. In, out is this, outflow. This is generation. This is recombination. So which option does tell us that? Rate of increase, inflow, outflow, generation minus recombination. So this will be your right answer. So you see the other things are very confusing. So be more vigilant. This is not true. Drift minus diffusion, not true always, because you need to take into account your generation and recombination also. So be more vigilant in answering this kind of questions in your semester exam or the term exam, whichever you are having in this October. Okay. So moving on to the next problem. Yeah, I think you can answer that. Let us let me allow you to try to solve this. What do you think? How should we proceed? This is very simple. They have told that assume an undoped gallium arsenide sample with the following properties of electron. Mobility is given, effective mass is given, and average velocity is given. They want us to find out mean free path. How should we go about this? Again, you know your mobility is what? Q tau over m star. Fine. So what you know from the question? Mu n you know it is given. M star you know given. Q you know. So you can find out T or tau. So what will be tau? Tau will be mu n times m star over q. So tau will be what? 8.8 into 10 raised to 3. Let me convert it into the meter scale because kilogram is sitting here. Meter square plus times volt second. What is in kilogram? It is 9.1 into 10 raised to minus 31 times 0.067. That is kilogram over what is Q? 10 raised to minus 19. That is coulomb. So tau will come out to be how much? 8.8 times 10 raised to 3 times 10 raised to minus 4 times 9.1 into 10 raised to minus 31 times 0.067 divided by 1.6 divided by 10 raised to minus 19. So you will have 3.35335 times 10 raised to minus 13 seconds. That is mean free time. Okay. So you want to find out mean free path. So your V average, you know, is your L average by tau. So your L average or mean free path will be what? V average times tau. What is V average? 10 raised to 7. That means 10 raised to 5 meter per second times 3.35 into 10 raised to minus 13 seconds. That will be 3.35 into 10 raised to minus how much? 8 seconds. That is 33.5 nanosecond. Okay. So this is how you are going to solve this kind of problems. These are pretty simple and we have done it multiple times. But this time you may get a shock by looking at the value of the mobility. See the mobility. What is the mobility value? Mobility value mu n is 8800 centimeter square plus per volt second. And what was the silicon mobility value? 1350, right, in bulk. So you see the difference. This gallium arsenide is a much faster device because of its mobility. Okay. So can you tell me what any another distinction between gallium arsenide and silicon?
Direct and indirect.
What does that mean?
Uh, uh, Silicon need both change uh, phonon and in I don't know.
No, try. Don't be demoralized. Try no.
Sir, it has indirect band gap means it need both energy to transfer. It need
So
change
let
of momentum also.
if this is a gallium arsenide, okay. So This is a EK diagram, okay? This is K, this is E, energy K diagram or band structure. So this is EC, this is EV. So you mean to say that EC minimum and EV maximum happens at the same K point,
Yes, sir.
right? So what does that imply? That if an electron is to jump from this place to this place, it does not require a change in K. Whatever you are, that is what you are telling, right? It does not need change in momentum or K, right? K is what?
Eh, P is equal to HK.
K is like crystal momentum, right?
Yes, sir.
Actually, P is crystal momentum. You can normalize crystal momentum, you can tell. So K is P by H bar, right? Okay.
Yes, sir.
So this is happening at the same symmetry point. So what happens is that the energy that due to this recombination will be leaving as h nu or photons. Photons do not need what? Photons, let's say, is considered massless, though it is not true always. So that is why I am putting the question mark. Photons is considered massless, so momentum is zero,
Yes, sir.
or momentum change is not required, right? So this is called direct band gap, and these are used in for
LED,
LEDs,
light
right?
emission,
And what about your silicon?
indirect band gap, semiconductor.
So it will be something like that, right?
Yes, sir.
This is your K, and let's say this is your energy. So EC minimum and EV maximum does not lie at the same crystal symmetry point or K value. Okay. So what happens from this place to this place? You need a change of delta K also. So that delta K change or change in momentum is conserved by some particle which can feel momentum change. For example, phonons, right? So that's why silicon is indirect band gap and cannot be used in photo generation, okay, or photon generation, or like cannot be used in LEDs, okay. So let's move on to the next part. So which of the following statements is not true about reverse bias breakdown? due to the impact ionization and Zener tunneling. So what are the types of breakdowns in a PN junction diode? Types of breakdown in a PN junction. What are the types?
Avalanche breakdown,
Avalanche breakdown and another one is, yeah, it will be a good revision for you. You can discuss, right? Maybe you are not remembering everything. That is very fine. You can guess and try to answer. It will be a good revision for you. What is the other type of breakdown? That is Jenner breakdown, right? So firstly, I will discuss what are the fundamental differences in mechanism of the Jenner breakdown and avalanche breakdown. First thing, remember that this is due to band to band tunneling. This is due to impact ionization. Okay. So let me first briefly discuss about Jenner breakdown. So what happens in Jenner breakdown? So the band diagram of a PN junction. Okay, let me go it step by step. The band diagram of a PN junction is like this, right? This is your depletion region. This is your EC. This is your EV. And let's say this is your Fermi level, EF, in equilibrium. Now, when we apply reverse bias, that means, let's say this is P, this is N. Reverse bias is what? There will be negative voltage, there will be positive voltage here, right? So how will the band shift? P bands will move upwards due to the negative potential, and right by this inside bands will move down. So we will have a situation something like this. This will be your EC, this will be your EV. This is your EC, this is your EV. What happens that this is your X depletion, okay? Electrons in the valence band can travel to this, and these electrons can move down the hill or energy barrier and come to this, right? This is one way how the electrons from this EV to this EC will transport. And what is the another way? Another way is that it can simply tunnel through this barrier. X depletion. Okay, this kind of tunneling is called band to band tunneling. Okay, when will this be more? When does generally tunneling becomes more significant?
Gap will be less.
Which gap? What is the value? What is the name I have written?
Uh, Depletion with.
Right, that is X depth, right?
Yes, sir.
BTBT or your Jenner breakdown. By the way, why it is called breakdown? Because in the reverse bias, there should not be any current flow, right? But
Yes,
as
sir.
now electrons can flow from this valence band to the conduction band of the opposite side, so carrier movement is continuous and there will be a huge amount of current flow. So that is why we call it as a breakdown. BTBT or Jenner breakdown happens when X depletion is lower, right? Are
Yes,
you
sir.
okay with that? So when
Sir,
will now take
BT.
band to band tunneling?
Yes.
So when will my X depletion be lower? Any idea?
Uh,
What is the
when
formula?
doping.
Yeah, tell me, tell me. Yeah, you are going right, right? Tell me.
Sir, same doping is less.
Uh, Now note that equation and tell me from this equation when X dep will be lesser, will be less when
Doping is
both
more.
sides, yes, both sides of the your P-N junction is highly doped. Okay, so this kind of question will come in your gate exam also, but then you
Yes.
have to use logic. That tunnel Jenner breakdown, first thing, Jenner breakdown happens due to tunneling through X depth depletion width. Depletion width will be lesser. I know that you have the understanding that lesser width will give me better tunneling, right?
Yes.
So then you need to find out that in which case this will be better. The depletion width will be lesser when both of the sides has to be highly doped, right? One side will not do. Both side has to be highly doped because it is 1 by Na and 1 by Nd, right? Both
Yes.
sides have to be highly doped. Remember, that is also a very important point. And also what happens that your Vr is preferred smaller, right?
Yes, sir.
Because with Vr your X depth will increase. So
Yes.
these two things, Vr smaller means what? Lower electric field comparatively. Okay, fine.
Yes, sir.
So this is about your Jenner breakdown. And what is the effect of temperature in that? Generally, T or temperature has very weak effect on Jenner breakdown. So this is your Eg. So this is take it as it is. If T increases, your Eg or energy band gap decreases or your tunneling will increase. Okay. So breakdown voltage decreases, right? In a lesser voltage, you will have better more tunneling. So it is said that Zener breakdown voltage has a negative temperature coefficient, or this you can say T increasing, breakdown voltage decreasing. That means your temperature coefficient of the breakdown voltage will be negative. Okay, this is how to analyze the Zener breakdown. Now in this context, I want to ask you a very conceptual question. If you have followed this properly, you can answer that. Okay, just try to answer that. It is not hard and fast that you should get it right, but try to answer that. Suppose you have a metal semiconductor Schottky barrier, which is rectifying in or which is this your Schottky in nature. Okay, Schottky barrier. How can you make it ohmic? Did you understand the question? There is a metal semiconductor Schottky barrier, right? So there will be some metal and there will be some barriers. Okay.
Sir,
So
same increase the doping.
okay, go on. So what will happen if we increase the doping?
Uh, then width will be decreased.
So this is your X depth. Let's say this is your metal, this is your semiconductor. Okay. So this is X depth. So in case of metal semiconductor, X depth is what? Root over 2 epsilon S phi Vi plus Vr times QNA or N, whatever the doping is, N depth, let's say, right? So if you increase your N depth, what will happen? Your X depth will decrease. So what will
Yes,
happen? As a result, tunneling will happen.
yes, sir.
What kind of tunneling will happen? Band to band tunneling will
Band
happen.
to band. Yes, sir.
And what will that lead to? That will lead to free movement of carriers, right? It will not
Yes, sir.
depend upon the barrier height. Very good. So this is a question which is generally asked in many interviews, okay? In BARC or this your IIT and PhD or MTech interviews, they ask these kind of questions. So this is very conceptual and depending upon what concept of the Zener breakdown concept, right? That
Yes,
why
sir.
we need high doped semi P-N junction for Zener breakdown. Okay. So now let us move to avalanche breakdown.
Sir,
Yeah,
this is what we use to in MOSFET to connect P plus and N plus use.
exactly. Exactly. Absolutely. Same concept, right? The metal
Yes, sir.
semiconductor you used, and then also the metal switch can be used to contact the source and drain P plus regions. And there are
Yes,
other reasons also, right? This is one reason, okay? Let's say these are the MOSFET contacts. This is P. Let's say this is the MOSFET and you have some kind of metal contact here, right? You are talking about this thing.
Yes, sir.
So as rightly pointed out, this is a MS contact, metal semiconductor contact, which is generally we made a ohmic contact. Okay. So this place we do it a high doping, and this contact also we make a high doping. The reason to make this contact high doping is one, to make it ohmic, absolutely what we have told, and another reason is to reduce the resistances of the source and drain region. What do I mean by that? Suppose you have a MOSFET like this, N plus, N plus. Okay, so if you apply your gate voltage here, sorry, your drain voltage here, VDS, let's say greater than 0, and this has 0. So where will the current will flow from which direction to which direction? This is your channel, right?
Yes, sir.
Now what happens that current is flowing through this path and moving out of this.
Yes,
Okay.
sir.
Now there is a resistance here. There is a resistance here.
Yes, sir.
So if this resistance is, let's say this resistance is RD, this resistance is RS. So what will be your current? You know this current is your ID, right? So if your VDS will be equal to what? ID times
RS
your
plus RD.
RS plus RD plus some channel resistance, right?
Yes, sir.
So if your RS and RD is more, then your current will be less for a
Yes.
particular VDS that you do not want. So what is R? R is equal to rho L by A. What is rho? 1 over sigma. And what is that? 1 over Q mu times N, right? So if your doping you increase, then your N is increasing. Then your rho is decreasing or your R is decreasing. So that is also another reason why you use highly doped contacts or diffusion regions for source and drain, right?
Yes, sir.
So these are the two-way thing. One is to make it a ohmic contact, absolutely what you have told. Another one is to reduce the series resistances. These are called series resistance effect. This the same thing happens in P-N junctions also. Okay, so that part I think the professor has covered. If you have forgotten that, you can just go back and look at that. In P-N junction, what do we mean by series resistance effect? Okay, so now let's move on to your avalanche breakdown. So what did we tell, that the important point is this is a method called impact ionization. Okay, let me tell you how does it happen. Let's assume that this is P region, this is N region, and these are the depletion region boundary. Okay, X dep, let's say. In reverse bias it will be plus, it will be minus. So holes will be moving in which direction? Holes will be moving in this direction. Let's say a hole is moving into this direction. Okay, what happens? It can, if it gets high energy, due to high electric field. What is energy in terms of electric field? It is Q into E, right? Q into electric field. Your energy is what? dE by
Q.
dx 1 by Q is equal to electric field, right? So if you have high energy, you will get, if you can somehow get high electric field in the around the depletion region, you will get more energy for these holes to move, and it can hit a silicon atom and bombard it and create an impact which may create an electron and a hole pair. Okay, this black spot I am drawing is a point of contact or point of impact. So the hole will then, the electric field is in this direction, so hole will try to move in this direction. But what about the electron? If the electron then will try to move in this direction, and let's say it finds another target, okay, and there it will create, let's say, another hole and another electron pair. So this electron will be swept away to the this n side, and this hole will then try to move here and create another collision. Again, this method will be repeated. Okay, so what happens is that in a very small amount of time or in a very small amount of space, the high energy holes and electrons which are being generated by the impact of another previous high energy holes and electron will create next impact, and that will create another impact and create another holes electron and hole pair. So in this way, there will be a avalanche or a huge number of, or a storm of holes and electrons. Okay, so then that holes and electrons will contribute to creating additional current, and that will lead to the breakdown. Okay, this is the mechanism of avalanche breakdown. So what are the points? Electric field needs to be high, that means it is a high VR or reverse bias mechanism. And what can you comment on X depth or depletion width? Should it be higher or lower?
Sir, um, it is independent of X depth.
No, it is dependent of X depth, right? Because suppose you are starting from this point, okay, and you have a larger distance to cover, then you will get a more momentum, more energy for the
Yes, sir.
particle.
Yes, sir.
Suppose
More
your
X depth.
more X depth, right?
Yes, sir.
So X depth should be more. And what is the condition on doping then for
Lightly
more X
doped.
depth? Exactly,
Lightly doped.
lightly doped. So you see the distinction, right?
Yes, sir.
For Zener breakdown, we need highly doped diode. That will
Yes, sir.
lead to tunneling due to the lowering of depletion width. But in case of avalanche breakdown, we need a higher depletion width, thus require a lightly doped PN junction. Okay, so remember this thing. So now going back to the question, it is mentioned that which of the things are not true, okay, in reverse bias breakdown due to impact ionization and Zener tunneling. So again, remember that these are just the different names of the same stuff which you know, avalanche breakdown and Zener breakdown. So first thing is that Zener tunneling breakdown generally occurs at lower voltage than impact ionization. Is it true?
Yes, sir.
So it is true. Zener tunneling generally has a stronger temperature dependence than impact ionization. Okay, let me tell you about the temperature dependence of the impact ionization. So, if temperature increases, what increases? Scattering increases. If scattering increases, then what happens? Your mean free path will decrease.
Yes, sir.
If mean free path decreases, then what happens?
Impact
Your
decrease.
impact ionization decreases.
Yes, sir.
If impact ionization decreases, then your reverse breakdown voltage increases.
Yes, sir.
More voltage will be required to create the same amount of impact.
Yes, sir.
So that means temperature coefficient is positive for impact ionization, impact ionization breakdown voltage or VBR, and temperature has a strong role to play. In Jenner, we had a temperature weak dependency, right? Weak effect. So, Jenner tunneling has a stronger temperature dependence than impact ionization. This statement is false, right? Impact ionization or avalanche breakdown has a higher temperature dependence. Okay?
Yes, sir.
And significant Jenner tunneling only occurs when the junction is heavily doped. Is it true?
True. True.
It is true. So,
All of the above.
no, we mentioned that which is not true. This one is false, right?
Yes, sir.
So, this will be the answer. Okay?
Yes, sir.
Okay. So, let's move on to the next problem. This part I have discussed in an earlier lecture, but again for the review, let me just tell this. For a PNP BJT, which of the following expression results the emitter injection efficiency? So let me draw a PNP transistor, PNP BJT. So this will be the depletion regions. So what is the doping? This is P plus plus, this is N plus, this is P. Remember that? So this junction is generally forward biased. Okay, or let's say VEB. And what will be the minority carrier concentration profile? Minority carrier concentration profile would be, let me just extrapolate the lines. We are concerned about emitter injection efficiency, so we'll be considering only about the emitter based junction. So minority carriers will be like this and drop like this in the base. So it will be delta P of B, it will be delta N of E. So these are the minority carrier concentration profile. Minority carrier concentration profile. So now if I draw the current flow diagram, remember that current flow diagram? So this is your emitter, this is your base, this is your collector. So this is positive, this is negative base. So what happens? Holes will get injected here, holes will get injected, and what will happen that electron will get injected in the base. Fine. So these holes will then move on. Some will be moving here. A portion of hole will be moving here. A portion of the electron will be moving this place and recombine with this. Another portion will be moving upward. Okay. So can you tell me the name of the currents? This is IE. This part is IEP. Fine. This current is flowing in this direction. This is also flowing in this direction. This is flowing in IEC. This is flowing out of the collector. This is what? This is some current will be flowing in this direction. This is IEN. And what is this current? This current will be IR. Okay. So your emitter injection efficiency is nothing but IEP over IE. Emitter injection efficiency. So your gamma will be IEP over IE, and if you apply your KCL at this node, you will find what? IEP over IE is nothing but IEP plus IEN. Okay. Okay. So your emitter junction efficiency would be IPE, same time they have used different terminology. So IPE over IPE plus INE, right? So this part we have discussed also earlier in another lecture. So for more detail you can refer there. Okay. So this question is that which of the following is not desired as a characteristics of a good voltage amplifier? Okay. So let's say this is a voltage amplifier AV. Okay. And it is driving a load RL. Fine. This is some sort of V in. Is that okay? This notation?
Yes, sir. Option B, sir.
How do you say that?
Sir, because maximum drop should be on RL. We need in output side, need that amplified output should be on RL.
So, but how, if you are to tell someone, how would you tell that? What you do, see the way to tell or in any interview or understand, correct way to understand is that this is a voltage amplifier in what sense? It is a small signal voltage amplifier.
Yes, sir.
Small signal voltage amplifier. So in small signal voltage amplifier, this what are the components? Only dependent current source will be there.
Yes,
Dependent
sir.
sources. That means linear elements.
Yes, sir.
Can we use Thevenin's theorem?
Yes, sir.
What about if you do not have any linear element? Can we use Thevenin theorem then?
No, sir.
Right. Remember that point always. So Thevenin theorem can be used. What is a Thevenin equivalent circuit of this? Some voltage source in series with resistance and then RL.
Yes, sir.
Okay. So you want maximum output at this node. And what is this RTH? RTH will be nothing but resistance looking inside. So this will be nothing but your R out. Fine.
Yes, sir.
So maximum output at the RL will be when R out is minimum, right?
Yes, sir.
So it is not desired, right?
Yes, sir.
So this is how you should think about all the circuits. Yeah, whatever you have told, that is right, but how to spell that out when you are telling someone if you are answering that in interview and all, you should tell that the amplifier voltage source, this is a voltage control voltage source kind of thing, or that is a voltage amplifier, that is a small signal, and that is linear. We can use Thevenin equivalent, and if we look into the output, we will see the output resistance, which is the Thevenin resistance, which will come in series with the load resistance. Hence, that Thevenin resistance should be lesser. Okay, fine.
Yes, sir.
Now tell me, in this regard, how will the scenario change? How will the scenario change if we have a transconductance amplifier? Do you know what is the meaning of transconductance amplifier? By the way, what is a voltage amplifier? It is a voltage control voltage source, right?
Yes, sir.
What is a transconductance amplifier? It is a voltage control current source, just like your
Yes, sir.
MOSFET. Okay. So the symbol is this. And let's say you have a load here RL. So in this case, what is preferred? What about output impedance? What should be ideal R out? Any idea?
We can think like that. This is current source, so it will be in parallel. So opposite will be happen.
So this is your V input, right? And what is the
Yes.
output of the amplifier? What is the output?
V input into GM.
GM into V in.
Yes, sir.
So we need this entire current to flow into RL, right?
Yes, sir.
So we do not need any output impedance. This will be my R out.
Yes, sir.
So we do not need any output impedance at this point. So what will be my no current should flow through this path.
Yes, sir.
So what should be my
Uh,
R out?
Infinite, ideally.
Ideally should be infinity, right? So that is why you remember that your MOSFET characteristics IDVD,
Yes, sir. Parallel to VD.
you had this kind of stuff. So this was This was my desired thing, right? Zero
Yes, sir.
slope. GDS equal to 0 or RDS equal to infinity, right?
Yes, sir. If no channel modulation.
If no channel length modulation. So channel length modulation, it's not desired, right? It's not desired.
Yes, sir. Yes, sir.
Okay, good. Good answer. By the way, whatever you have answered is also correct. Okay, you can think it as
Yes,
a
sir.
current source where the non-ideality comes in terms of a resistance in parallel to the ideal current source, right?
Yes, sir.
That is also a good way of thinking. So again, moving on to the problem number 8, which of the following condition represents the pinch-off point in a MOSFET? We have discussed this in 2 weeks back.
VDS equal to VT.
What is the pinch-off?
Before channel just formed.
No, that is threshold. What is
Sorry.
pinch-off?
Pinch off. It saturate. Means channel length.
Try to tell. No issues if you get it wrong. I know you know the answer, but you are not able to say it. Pinch-off is this, right?
Yes, sir.
When at drain end,
Resistance is very high or
no,
presence
no.
of electron
When
is
when
very
at
low.
drain end, inversion charge is what? Zero.
Uh, Zero.
Just zero.
Yes, sir.
At this point, inversion charge is just zero, right?
Yes, sir.
So, what should be the voltage there? At
VT.
the voltage there should be VT, right?
Yes, sir.
Is that so? Okay, just let me explain it in this. So I think this needs some. So this is your oxide, this is gate, and this is the channel, right? This is the channel, okay? So there should be some potential. This potential of the channel is varying. Let's call that potential to be VCH, okay? This is X direction and VCH is varying. Fine. Now it is VG and it is VCH. What will be what is the potential at this point?
Source potential VS.
What is the potential at this point? VD.
VD.
So what is the effective potential from gate to channel at this point? Basically VGS minus VCH X. This is the effective potential, effective or I would say gate voltage. So at source end it is what? Vg minus Vs.
Yes, sir.
At drain end it is Vg minus Vd. So at drain end I need what? Inversion charge to be 0. That means this stuff need to be threshold voltage equal to threshold voltage.
Yes.
Are you understanding?
Yes, sir.
So my what should be my Vd? Vg minus Vt. Now if you refer everything in terms of source, so you can simply write that.
Yes, sir.
Okay. So this
Yes,
is
sir.
how the actually you see when you increase your drain voltage, right? What happens is that this potential starts to increase. That means this start to increase. So effective Vg minus Vd start to decrease, and at a point it becomes equal to threshold voltage. Then the channel just touches the drain. That is called pinch off. Okay.
Yes, sir.
So this option would be right. Is it not?
Yes, sir.
Another way to think of is pinch off is the VDS equal to VDS sat. That is your VGS minus VTH. Okay. This is this point when my this start to saturate. Okay. So let's move on to the next point. The next question. Which of the following statements is false? For a common source amplifier with resistive load, voltage, what is a common source amplifier? This is a common source amplifier, right? V in source is common, and if you have some VRD, and you will have some VDD here. So what is the gain of this amplifier? GM times RD.
Yes, sir.
Sorry, RD. Let me correct it. RL. GMRL.
Yes, sir.
So GM is what? We know that GM is mu n Cox W by L VGS minus VTH. We know that, right?
Yes, sir.
ID equal to half mu n Cox W by L VGS minus VTH whole square. GM is equal to DID by DVG, right?
Yes, sir.
So that is from where this will come. So GM is proportional to W and GM is proportional to 1 over L. Can we write that?
Yes, sir.
So for a common source amplifier with a resistive load, voltage gain can be made high by increasing the channel width of the MOSFET. That is true.
Yes, sir.
This will increase, modulus of this will increase if GM will increase, if GM will increase when W increases. Similarly, if L decreases or channel length decreases, GM will increase and the gain will increase. So this will also be true. For a BJT to be biased in active mode, base emitter junction is to be forward biased, true, and base collector junction is to be reverse biased, that is also true.
Yes, sir.
A MOSFET used as a switch is generally biased in the saturation mode of operation. Is that true?
No, linear mode of operation.
Why?
Because linear mode it require less time to switch on and switch off.
Why?
Uh, uh,
So this is a bidirectional, this is a, let's say this is source, this is drain, okay?
when you draw the that I V versus I curve, that is linear, so resistance is small, and here resistance is infinite, so less resistance.
Why do we need less resistance?
Time constant RC is R is less than RC is less.
So R1 we need to be lesser, right? What is R1 here? R1 is nothing but 1 over GDS, right? At this point, GDS is lower.
Yes, sir.
So there is a resistance, right? Across
Yes, sir.
this. And what will be the signal? Let's say from an antenna, a signal is coming here, and here is some amplifier, some next stage LNA amplifier or low noise amplifier, some kind of amplifier is there, okay? So signal needs to travel from this place to this place. So it needs a lesser resistive path, okay?
Yes, sir.
So that is why it is operated at around your VDS equal to 0, this range. or in a linear mode. Okay.
Yes, sir.
And also another one which you have told, that time constant, that is not actual, that does not signify any effective time constant. The time constant what you are talking about is your R on times C off. Okay.
Yes,
What
sir.
is that C off? That C off would be whenever this gate is, say this is the on condition. Okay. Whenever there will be a off switch or gate is off, let's say, then there it will act as a capacitance, CDS, drain to source capacitance. So this product determines the speed of the switch. Okay. Or in higher terms, terminologies, this R1 will translate to your something called insertion loss. This C off will translate to something called isolation. This you will learn in later courses. Okay. So this R1 C off is a very critical parameter for any switch application. This R1 C off, which is a time constant equivalent, has to be lower. So that can be lowered by either by lowering R1 or C off. Okay.
Yes, sir.
So R1 can be, R1 you can increase or you can R1 you can decrease by increasing the width of the transistor. Okay.
Yes, sir.
But what will that impact? That will impact your C off to get increased, capacitance to increase, because C is epsilon times A into D. That A area, there the width will come. So in a sense, you remember that R1 C of product needs to be lower. And basically to lower the R1, we need to operate in the this region. This region. Okay. So this
Yes.
is the correct answer. So this is false. So which of the following statements are true? Presence of interface traps does not affect the subthreshold swing of a MOSFET device. That is wrong. Why? Because we know SS is equal to phi t ln 10, phi t ln 10, 1 plus C depletion plus CIT over Cox. This we have done in last class. This CIT is the interface trap which will change my subthreshold slope. So this is not correct. Channel length modulation has impact on the slope of output characteristics of the MOSFET. This is true.
Yes, sir.
Presence of gate drain overlap gives rise to additional parasitic capacitance in a MOSFET device. That is true. What does that mean? That means that if you have
Over, overlap
this,
capacitance.
yeah, if you have some oxide like this is drain, this is source, this is P type. So you will have these overlap regions, right? This will lead to a capacitance. These are the parasitic capacitance. This is called CGSO, CGDO. These are the main parameters of controlling these capacitances. CGDO and CGSO. O stands
Sir,
for overlap. Yeah.
sir, it is sir, it is manufacturing error that overlap is there, or uh, we
It is
knowingly do
no.
overlapping.
We do not want this. This is parasitic. Parasitic means what is parasite means. Malaria is a parasitic disease, right? That means the
Yes,
parasite we do not want. Parasite means something we do not want.
yes, sir.
So this we do not want. Parasitic capacitances we do not want. Why do not want? Why do we not want that? We do not want that because it increases the poles in the circuit, or RC time constant it will increase, right? So your device becomes more sluggish or slower. So you do not want any kind of capacitances. It is just a manufacturing error, because how will, if you look at the from the top side, you will see something like this, right? This will be your gate and here you will get your source and drain multiple source drain contacts. Okay, but what happens that this gate region will have a overlap with the source regions. Why? Because it is very hard to make sharp corners in any kind of your this stuff. What do you say? The main reason of this error is that suppose you have taken a wafer, okay? Now you will diffuse your source and drain, right?
Yes, sir.
So you need to make rectangular contacts on the your this what is that mask, you know, right? Where the
Yes, sir.
patterns are made in mask, you will be making rectangular openings for source and drain. But will that be normally, will that always be rectangular? This, so this will spread, this will laterally spread, right?
Yes, sir.
So this lateral spread will cause your this gate and source to get overlapped. So remember that no process is absolutely perfect, but nowadays instead of diffusing these things, we use ion implantation. Okay, that also creates certain amount of lateral diffusion, but that can be reduced. That is much more reduced than the case of when we used to make the source and drain contacts using diffusion process. Okay,
Yes, sir.
and also you cannot afford to make your gate smaller than your source and drain. What will happen then? There will be a gap where there will be no channel or the no field effect, right?
Yes, sir.
So that is why there will be certain overlap region always in any form of device you can take.
Yes, sir.
Okay, I recently had encountered some exotic devices where what they do, they wrap the gate around, but they do not wrap, they take the substrate and dig a hole, and in that hole they put the gate material, and on top of that and bottom of that they put the source and drain contact. In those kind of cases there is no overlap capacitances. These are in some kind of high end ferroelectric field effect transistor stuff. Okay, but yeah, that is also, keep it in mind that there are some exotic new structures are coming or manufacturing processes where these overlap capacitances can be avoided. Okay,
Yes, sir.
but those may not be for the mass production or a huge number of transistors. There may be some specific niche applications. Okay, so in the absence of channel length modulation effect, the saturation drain current in a MOSFET is independent of the applied drain to source voltage. That is also true. So this is true, this is true, this is true. So 2, 3, 4 are true. Okay.
Yes, sir.
So that is all for today. So if you have any question,
No, sir.
okay. So thank you. So let's end the session today.